All right, let's go through the chapters 7 and 8 problems. So number 12 is kind of a warm-up, and we can see that it's 0 meters per second squared for 12A because it's going at constant speed. Constant speed means that it's not accelerating. Now for B, it's pretty much just plug and chug. We've got a force and we have a displacement. Force times displacement is 33 joules. Now in 18, we have a force being applied at an angle. It tells us that it's a 30-degree angle. And so we need to find the component of that force which is in line with or parallel to the displacement. So we just do F cosine theta S. Plugging those numbers in, we end up with 8.7 megajoules. All right, in 23, it says starting from rest, a 25 kilogram kid runs up a 5-meter long slide. At the end, he is standing still 3 meters higher than at the start. How much work did he do? What they're trying to emphasize here is that when you're working against gravity, all that matters is the vertical displacement, since gravity is always working or acting straight down. Okay, so we just do mgh. Mg is a force. It's the force of weight. Height is a distance. Force times distance is work. And so we have 0.74 kilojoules. Now in 31, we've also got we have a force acting at an angle again. So let's look at 31A. There's no net force to cause acceleration. Now, how do we know that? We know that because it says being dragged at a constant speed. Whatever force is being used to drag it one way, it's being overcome by an equal and opposite force of friction that's going the other way. Okay, so for B, it's asking us what is the magnitude of the component of the tensile force parallel to the floor. Of course, we need to know that because we have to be able to compute the work. So we have our F cosine theta again, and that turns out to be 8.66 newtons. And finally, it asks us for the work. So we take that component we found and we multiply it by the displacement to get 26 joules. All right, so in 35 is talking about the men's world swimming record for the 15-meter freestyle. And it tells us what the average speed is. Now, since we're given a mass, we can put this in terms of kinetic energy, 1/2 mv squared. And then we just plug and chug to get 197 joules. Up until now, we haven't really had any tough problems in this particular problem set. But what's important is that you understand the concepts of work and energy. Okay, number 42. Suppose that a 0.149 kg baseball is traveling at 40.0 meters per second. How much work must be done on the ball to stop it? So this is negative work. And we call it negative work because the thing's already in motion. We're going to bring it to a complete stop. So if that thing had 119 joules positively, if we want to bring it to a stop, we need negative 119 joules to bring its energy to 0. Okay, now the next thing that we're asked for in 42 is if it's brought to rest in 2.0 centimeters, what average force must act on the ball? Okay, so we know that we have a deceleration here. So we need to find that deceleration. We use Vf squared equals Vi squared plus 2As, plug in our givens, and we find the acceleration is negative 40,000 meters per second squared. Notice I'm not worrying about significant figures yet. We do that at the end. And then since we're asked for the force, F equals ma, we put in the mass, and we find that the force is 6.0 kilonewtons. Now, on a test, if you put negative 6.0 kilonewtons, I would certainly accept that. But I'm just making it positive for convenience in this case. So don't worry about the sign too much. But if you wanted to be, if you wanted to write it negative, then I simply, wouldn't care. That would be fine. All right, number 49. What we have here is another kinetic energy problem. And it's talking about a golf ball that's driven from rest to a fast speed of 70 meters per second. And that acceleration takes only 1.0 milliseconds. Okay, now they want us to find the kinetic energy of the ball. So we just do 1/2 mv squared and we find 0.11 kilojoules is the answer. And then the next question is the approximate distance over which the club acted on the ball. So there are a couple ways to do that. I put a harder way and an easier way here. We could do VF equals VI plus AT. 7 equals 0 plus 8 times 0.001. We do that to get the acceleration. And then we can do VF squared equals VI squared plus 2AS in order to find the displacement. Now, the other thing we could do is just do S equals 1/2 VI plus VFT. And that's going to give us the same displacement of 3.5 centimeters. Remember stuff that we learned earlier on when we were doing our acceleration equations. Those are things that we're going to be using really throughout the year. Okay, number 61, I'm deciding to skip. Not because it's a bad problem, but just because it's unnecessary. If you want to do it just for fun, well, I'm briefly going to let this be, or let the camera be over the solution. But if the solution doesn't make sense, don't worry about it. We are skipping that problem. Okay, let's look at 73. Now, 73 is an example of conservation of mechanical energy. And we're going to see this concept as well throughout the year. It's a very important principle. It means that the total kinetic energy and potential energy in a system is conserved. The final state matches the initial state. Okay, so what they're asking us for in 73 is we want to see if there is sufficient energy to make it to town. Now, what that means is that it's got to be able to go up the hill. So we ask ourselves, all right, well, given those speeds, right, is it going to be able to make it up the hill? Now, notice how they're kind of adding information here that you don't need. And the reason they're doing that is because they just want to make sure you understand the concept. So the 7.12 kilonewton and the 4.24 kilonewton, that is completely unnecessary information. Why? Because gravity acts equally on different masses. So we set up the conservation of mechanical energy equation. We know that when the car cruises to a stop, its kinetic energy final will be 0. It's going to have an mgHf, that is a final height that it rests at. And it's going to have an initial kinetic energy, 1/2 mvi squared. It's the speed it starts with before it begins to coast. And it's got an initial potential energy, which is 0 because it hasn't gone up the hill yet. Then things cancel and we end up with GH max equals 1/2 VI squared. If you wanted to just do GHF instead of GH max, that's fine. It's just a question of symbols. It doesn't really matter. And then you do some plugging and chugging. We did convert that speed that was given in kilometers per hour. We converted it into meters per second. And we find that the height reached will be 36 meters. Now it does say 33.5 meter high hill. And even though this hill is lower than the maximum height, well, that's fine. It means that it's going to be able to get over the hill. easily with a little bit to spare. Okay, number 76. Again, this is a conservation of energy problem. And it says a kid in a wagon is traveling 10 meters per second just as she reaches the bottom of a hill and begins to climb a second hill. How high up it will she get before the wagon stops, assuming negligible friction losses? Okay, so the setup's pretty similar to the last problem. We have our final kinetic energy state, and we have our initial kinetic energy state. Let me just move that a little bit. And we just fill in the things that we can. Now, even though you can see that it ends up being GH equals 1/2 V squared, I really think it's a best practice to lay out everything for two reasons. One is to avoid silly mistakes, and the second is just to reinforce this concept that energy is being conserved. It's a lot more effective to do that than just memorizing formulas all the time. Memorize a few, but don't memorize every possible formula that you can. Okay, now we put a few things in. We have 9.81 HF equals 1/2 times 10 squared. And so the final height's going to be 5.1 meters. Okay, in 76, a ball having a mass of 0.5 kilograms is thrown straight up at a speed of 25.0 meters per second. How high will it go if there is no friction? If it rises 22 meters, what was the average force due to air friction? So we're going to do this in two parts. We're first going to do it neglecting friction. We set out the conservation of mechanical energy equation, put in what we can, and we can see that if it goes up with an initial velocity of 25 meters per second, it's going to slow down and will come to a stop at 31.9 meters. It comes to a stop when there is a zero kinetic energy. That's why we put in 0 to fill in for KEF right here at the top. Notice that KEF is replaced with 0. This is a weird little pencil with strange sharpening and a string hanging on it. Okay, so that's 76A. Now let's go to 76B, which is a little more tricky. Okay, and let's make sure we understand what's going on here. So mgh prime equals 1/2 mvi squared minus the force of friction times h prime. We're saying h prime because the h that we found without friction was 31.9 meters. But in 76b, clearly it's not reaching the height of 31.9 meters, because now in 76b, we are taking friction or air resistance into account. Okay, so what we do is we say, all right, the final kinetic energy that this thing ends up with when it's a certain height above the ground has to equal the initial kinetic energy that it had minus the work done by friction. FFH prime represents the work done by friction. Notice it's a negative work. It takes away energy. Then we just plug and chug and find that the force of friction is 2.2 newtons. So as it was going up with its initial velocity of 25 meters per second, air resistance was slowing it down at 2.2 newtons. And so it reaches a shorter height than it would have without the air resistance. Okay, 93, we're now moving on to the concept of power. Power is just work over time. And it says the energy expended in doing one push-up is about 3 times 10 to the second joules. How much power is needed to do one push-up per second? How much power must be developed if someone is to do 10 push-ups in 5 seconds? Don't worry about the develop thing, it just means used. All right, so in 93A, we simply do work over time. And so 3 times 10 to the second joules divided by 1 second is 3 times 10 to the second watts. Now in B, it's 10 push-ups in 5 seconds. Okay, so we multiply the amount of energy of a push-up. We multiply that by 10 because there are 10 push-ups. The time is 5, and we end up with 6 times 10 to the second watts. 95, a runner traverses a 50-meter long stretch on a horizontal track in 10 seconds at a fairly constant speed. All the while, she experiences a retarding force of 1.0 newtons due to air friction. What power was developed in overcoming that friction? All right, so work equals force times distance or displacement. And we plug and chug, find that that's 50 joules. And since it tells us that it was 10 seconds, work over time is joules per second, and that's 5.0 watts. That brings us to our last problem. Number 100. A 17.8 kilonewton car is to be accelerated from 0 to 96.5 kilometers per hour in 10 seconds. Neglecting all frictional losses, how much power must be supplied in the process independent of the exact nature of the acceleration? Incidentally, air friction increases rapidly with speed, becoming a major concern above 64 kilometers per hour. So air friction is very dependent on speed. When we were doing projectile motion, I think I mentioned this briefly in the lab, that we get a perfect parabolic shape if we're just tossing a ball underhanded, or even, shooting a free throw, whatever. Those are slow speeds. But if we are pitching a baseball or hitting a baseball, anything that involves fast speeds, then air resistance kicks in really fast, and air resistance goes up as speed goes up. Okay, there is a long way and a short way. I want to show you both because I think it helps us to learn more. First, let's look at the long way. We find the mass, because we can do Fw equals mg. Then we do Vf equals Vi plus At in order to find the acceleration, 2.68 meters per second squared. We then find the displacement, 134 meters. We use Newton's second law, F equals ma. We do that because that's going to give us the force. The force times the distance divided by the time will give us the 65 kilowatts. And so we've answered the question. That's the power necessary. Now there's also the short way. Let's look at the short way. Obviously, if you were to choose one or the other on the test and you chose the short way, that would be fine. There'll be no difference in which one you choose. But I'm intentionally showing you both because it helps our learning. Okay, so the other way to look at it is this. The final velocity after the acceleration is finished, right, is 26.8 meters per second. Now, that means there's a certain kinetic energy. That kinetic energy is 1/2 mv squared, giving us 651,614 joules. Okay? And then we do work over time and find that it's 65 kilowatts. Notice that 65202 is not the same as 65161.4, but with significant figures it ends up being the same. And the only reason it's not the same is because if you look at all those calculations we did, right, and the fact that we use 9.81, which is an approximation, we're going to come out with something that's a little tiny bit different. But with significant figures, we end up with the same answer. All right, so that's it for the chapter 7-8 problem set. This week, I'll also post an optional review set. And of course, we'll have our review game before the test, which will cover chapters 7 and 8. And we'll also cover chapter 6, part 2 with chapter 12. We're going to call that the chapters 6 through 8 test. Okay, see you in class.